All right, welcome back. We're going to start chapter 7. All right. Now, so far, we've been dealing with kinematics in the beginning of the course, and you were supposed to do that over the summertime, and you talked about kinematics, which is study of motion itself, right? It pretty much studies how things move and the behavior of the motion, right? But we never really talked about like what caused that motion. And that's when the dynamics came in. The forces, any push or pull pretty much caused objects to have motion, right? Now, once we have that motion caused by that force, we're actually giving energy into that force, right? I mean, not force, energy into that object, okay? So we're going to combine kinematics and dynamics, and then we're going to talk about work and energy. All right, so that's the new, I guess, chapter or unit in our physics. Now, when you have to work, what happens? What do you get? Right? When you have to work, when I have to work, I get mad. Come on, we all get mad, right? So when you have to work, you get mad, right? Well, work then is equal to force. So MA is force dot displacement. So they knew work is equal to man before even Newton. Wow, it's amazing, right? So force dot D is equal to work, okay? Now we know force has unit of newtons, right? And you know displacement has unit of meters. Therefore, work should have unit of Newton meters. Well, they decide to give this unit to joule. Okay. Now, 1 Newton meters and is equal to 1 joule. Joule is capital J. Okay. So when you push onto something or pull something, right? You are actually giving some push to make this object either speed up or slow down, right? So when you give some um, force, you're either making it go faster or slower. So work done by a force will transfer right, energy into an object, right? Or or take away from an object. Okay? When you are putting energy into an object, you'll get positive energy. When you take away energy from an object, it is a negative energy. Okay? So when we talk about motion and energy, we're really talking about only one form of energy, which is called kinetic energy. Okay? And I'm going to introduce you to that word now, might as well. Now, kinetic energy is energy of motion. So when things are moving really fast, right, we have lots of kinetic energy, right? If we're moving slow, right, we have a little kinetic energy. Stop, right? If it's stopped, no kinetic energy. Yeah, it's like Kim's Convenience. It's like, stop, right? When it's stopped, no kinetic energy. All right? The more speed an object has, the more kinetic energy it carries. Okay? But direction does not matter, and that's so important. Direction does not matter because energy itself is a scalar quantity because it is calculated using a dot product. So never ever have this x hat, y hat, z hat John attached to work or energy. Okay? So a new way to talk about what forces do to objects is what energy is all about. So we say when energy is transferred to an object, it speeds up, right? And that is pretty much positive, right? Positive joules. And when we say when energy is transferred away from an object, it slows down. That is the negative joules, right? And that is important. So forces act on objects, making them speed up or slow down. So we will say that forces are the things that transfers energy into or away from an object. Okay. We also say that when forces do work, right, they transfer energy into or away from an object. So we will be able to calculate the work done by the force on an object, and we will see that this work done will equal the joules of energy transferred to or away from the object. All right, all right. So how do we calculate work? Remember I said when you have to do work, you get mad? Well, here's some more mad things you have to do. Ready? Mathematical definition of work is basically dot product of force and displacement. Okay? So we will start only by looking at constant force. So this is a force that is constant We could later on see that force can be varying force, right? Then it gets a little bit more complicated, but the concepts are the same, right? So this work is really, really equals to, because there's a triple equal sign right here. So it means really, really equals to, or it could mean mathematical definition as well. Force dot. This is a dot product. This is a dot delta x. This delta x is change in position only along the x direction, right? So if it's only moving along the x direction, or if it changed its position along the x direction, then you use delta x. But you know this is AP1, so we're going to be in multi-dimension. So force can also equal to F, right, dot delta R, because delta R is change in position out in space in x, y, z coordinate system. All right, so don't limit yourself to one-dimensional, right, line. Be three-dimensional. It's really cool. Yeah, right. Now we all know from chapter 3, the work, the dot product itself is the magnitude of the force times the magnitude of the displacement, right, times the cosine of the angle between F and delta R, right? That's definition of dot product. Okay? If you think about it, force magnitude can never be negative because it's a magnitude. So it is square root of, right? Fx squared, Fy squared, Fz squared added up. Delta R can never be negative because it's a magnitude of delta R. So Rx squared plus Ry squared plus Rz squared square rooted. So that can never be negative. Cosine of theta is the only thing that can make this work positive or negative. Because if it's anything between 0 and 90 degrees, your cosine of 0 and 9, between 0 and 90 will be positive values. At 90, it'll be 0. And anything greater than 90, so between 90 and 180, this cosine of that angle will be negative. Okay? So this is okay? And of course, the unit for force is in newtons, and delta x is in meters. Therefore, this will be Newton meters, and that is same as joules. And that is just simply capital J. So, how to take the dot product of any two vectors. We should know this, but quick. So here, I have two vectors. We have force vector and we have displacement vector. Okay, displacement vector delta x because it's along the x direction. So first step is to draw vectors from a common origin. So first draw the vectors out. So here's my force vector. And here's my displacement vector. Okay, so that's my displacement vector along the x-axis. Here is the common origin, right? And this is the angle theta, right, between F and delta x. Now, obviously, in more general terms, right, this can be orientated whichever you want, really, right? It doesn't always have to be, you know, on the x-axis. Matter of fact, your force vector can be out in space like this, and your displacement vector can be also out in space like this, right? So it would always be, depending on how you look at it, it would always create a plane between F and delta R, right? So this plane that this F and delta R creates will always have force and delta R angle like so. It doesn't always have to be, acute angle like this. It could be like this, right? It could be like that. So sometimes, depending on how you look at it in three-dimensional space, right, you always have to find this plane as your theta, okay, or this. But if it's like this, at 90 degrees, your work will always be zero, okay? So your work, right, is equal to, right, F dot delta x. So I think the best thing to do is just look at an example. Let's put some numbers in here. Let's say force is equal to 40 newtons, right? 40 newtons. And this angle here, let's say, is like 30 degrees. And let's make your delta x to be 25 meters. It's only along the x direction, so x hat. Okay? So, if we want to find work, right, on m by the force F, right, is equal to, since it's a dot product, it's the magnitude of my force times the magnitude of my delta x times the cosine of the angle theta between F and delta x. So here, my force happens to be 40 newtons, and my delta x happens to be 25 meters, and the cosine of angle 30 degrees. So if you work it out, your work on m by F is equal to, cosine of 30 is like 0.866, and it's positive, right? Times this would be positive 866.0 Newton meters. Now notice, no x hat, no y hat, no z hat, nothing. So don't get confused with dot product with cross products. And you could also say work on m by F is equal to positive 866.0 joules. Same thing. Okay, they're exact same things. Okay? So it's easy to find, right? It's easy to find work done by one force, right? But what about when there are multiple forces? Then what? You have to find all the work done by each individual force, and then add them up. And what happens when you add all the work up? You get network. Get it? Network. Work net is what you get, right? So the network, right, is sum of all work basically done by each individual forces. Okay? So since we talked about, like, how work can be positive or negative depending on the angle between the force and delta x, right? If we find all the individual work done by individual forces and then add them all up, we can get ourselves a net work. So for example, force 1 dot delta x. Now force 1 dot delta x, whoa, this cannot be 40 newtons. That should be 40 meters, not newtons. So even though this force 1 is working on this mass to go 40 meters this way in the positive x direction, force 2 has the same common delta x, same as force 3 and force 4. The delta x is common for all those forces, right? So if you were to look at this, the force 1 will do simply work 1, right? So this here would be just work 1. And this here will be work 2. And so on. This would be work 3. And you could add them all up, right? To get your network or work net. All right? Sometimes this could be positive, right? This could be positive, this could be negative, this could be negative, and so on. You just add them up, whatever you get, positives and negatives. Okay? So to do that, what you need to do is you need to figure out what work for each individual one is. So we're going to go from 0 to 40 meters in the positive x direction. So our delta x will always be positive 40 meters in the x direction for all these four forces. So let's take a look at what happens. Now, follow me with this and see if you can divide this page into half right here and only write only this side of the page for now. So I'll show you why. So here, if we were to find work 1, okay, if we were to find work 1, so work 1 is equal to, right, F1 dot delta x. Now F1 is 5 newtons times delta x is 40 meters times the angle between F1 and delta x is 0 degrees. So it's cosine of 0 degrees. Okay? Therefore, if I work this thing out, this is 200 times cosine of 0 is 1, so I get positive 200 joules. Work 2 is equal to, right, F2 dot same delta x. Therefore, it is 6 newtons times 40 meters times cosine of. Now the angle between my force 2 and delta x happens to be 50 degrees. So it's cosine of 50 degrees. So if I work this out, you'll get positive 154.27 joules. All right. Work 3. Similarly, you get F3 dot delta x, and that is equal to 2 newtons times 40 meters times cosine of. Now, you got to be careful here because this is not cosine of 20, but this is cosine of 160 degrees. Okay. And since this is bigger than 90 degrees, you know it's going to be zero, negative number here. So negative 75.18 joules. Then your work 4 is equal to F4 dot delta x, and that is equal to 2 newtons times 40 meters times cosine of 180 degrees. Therefore, this is negative 80 joules. So if you work it out, your net work is equal to work 1 plus work 2 plus work 3 plus work 4. And that is equal to, right, 200 plus 154.27 minus 75.18 minus 80. And you should get your net work. And that comes out to positive 199.1 joules. Right? Right. Okay? So that was easy, right? That was easy. But this is actually pretty easy because it's only in 2 dimensions. Because you know everything's all in flatland here, right? But what if these were out in space? And instead of 1 meter going, F1 going positive x hat only, what if it's like going out here like this or like that? And then this one's like going into the page like this, sort of skewed out. And that's going to be messed up, right? So if that's going to happen, what you should do is you should think about using my net work is basically, if I were to factor out the delta x in all this and add up all my forces first, that's nothing more than just net force dot delta x. The net force is adding up all the forces first. So to do that, it might be a good idea to put all these forces in a Cartesian form. Okay? So if I were to find the F1 in Cartesian form, that's pretty easy, right? Your F1 really is equal to just 5x hat plus 0 y hat newtons. Right? Your F2, right? Your F2 is really nothing more than 6 times cosine of 50, right? Which is 3.86 x hat, right? And then 6 times sine of 50, which is 4.6 y hat newtons. And then for F3, right? F3, you have 2 times cosine of 160, which is negative 1.88, right, x hat, and then plus 0.684 y hat newtons. And F4 is easy, because that is just simply negative 2 x hat plus 0 y hat newtons. Right? So to find the net force, all you have to do is just add these four forces in the Cartesian form, right? So your F1 is 5x hat plus 0 y hat. Your F2 is equal to 3.86 x hat plus 4.6 y hat. Your F3 is equal to negative 1.88 x hat plus 0.684 y hat. And your F4 is equal to negative 2x hat plus 0 y hat. Okay? And if you add them all up, you get your net force. And your net force is simply 4.98 x hat plus 5.284 y hat. So once you have this net force, now you can calculate the magnitude of that net force. And that is simply square root of 4.98 squared plus 5.284 squared. And that comes out to, I believe, 7.26 newtons. What about the angle? Theta is equal to tan inverse of, right, 5.284 over 4.98, because it's in first quadrant. And if you work that out, your theta comes out to 46.7 degrees. So your net force is actually this. This is your net force right here. This is your F net. And that is equal to, right, 7.26 newtons. And the angle here, theta, between F and delta x happens to be 46.7 degrees. So now you can find net work, right? You can find work net is equal to, right, the magnitude of F times the magnitude of delta x times cosine of theta between the net force and delta x. Therefore, your work net is equal to 7.26 times newtons times 40 meters times cosine of 46.7 degrees. And if you work that out, and guess what? You get something like 199.17 joules, which is close enough to 199.1. Right? Voila. Okay? So that wasn't that bad, right? All right. Any questions? All right. The next page is very simple. It's simply this. Right? So there's two ways to do a dot product. Remember, when we were actually doing dot product, we could do it magnitude times cosine of the angle between. Or we can do, remember, x times x plus y times y plus z times z. Right? So here's another way of doing a dot product where you can actually find the net force. Right? So find the net force. And that comes out to, if I add just the forces up, I should get 4 I hat minus 13 j hat. Right? And since work is equal to the net force dot delta S in this case, right? That is simply saying that net force X times delta S X plus the net force Y times delta S Y. Remember that for dot product? If not, make sure you take a look at chapter 3 again. So here, delta Fx is 4 times delta Sx is 5 plus net force Y, negative 13, times delta Sy, 6. So if you work it out, you're going to get 20 Newton meters minus 78 Newton meters, and that comes out to negative 58 joules as my work note. Now notice that negative joules means that's how much energy right was transferred away from the object. Voila. That's it. Any questions? All right, so I'm going to stop the lecture here.